Now we're going to talk about higher order derivatives. I touched on this a little bit earlier when we looked at the relationship between position, velocity, and acceleration, but now we're going to look at it more in general terms and not necessarily in terms of applications. So we want to understand that higher order derivatives exist and how to find them. Okay, so higher order derivatives. All that means is we can continue to take a derivative of a function until we can't anymore. And some functions we won't be able to anymore. So for instance here, I have the function f of x equals x to the fourth plus 3x squared minus 8. So let's go ahead and let's find f prime of x. So f prime of x is going to be 4x cubed plus 6x. Alright, hopefully that's pretty straightforward. Now let's find f double prime of x. All that means is find the derivative of the derivative. Notice the notation, so we can keep adding these primes, or if we, instead of the dy dx, it's d squared y over dx squared, it's not really squared, I apologize, I shouldn't say that, it's d to the second y over dx to the second. It's a notation thing, it's not telling us that we're squaring it, so we actually don't want to think about it that way. But the second derivative, so just do my power rule again. So 4 times 3 is going to be 12 x squared plus 6. Let's do the third derivative. F triple prime of x equals 24x. And now notice this, the notation for the fourth derivative, we stop using the primes because at some point you're just going to have a ton of primes there, and that's just going to look really confusing. So once we get past the third derivative, now we just put a little number there. But notice that we put it in parentheses, so again, it's helping us understand it's a notation for derivatives, it's not an exponent. So then if I do f4 of x, that's just going to be 24. And notice that if I was to do the fifth derivative, or any other derivative after this, I'm just going to get 0. Because as soon as I get down to a constant, the derivative of a constant is 0, and so then I'll keep getting 0. So the fifth, the sixth, the seventh, the 8th, the 100th derivative of this function is just going to be 0. Another thing I want to point out, okay, so the process, hopefully that's pretty straightforward. You just do a derivative again. But it's important to understand the relationship between these functions. So we talked about, and we'll talk about this again at the end of this video, the relationship between position, velocity, and acceleration. So that's with context. But even without context, we want to understand that, for instance, the third derivative right here, this is the first derivative of the second derivative, right? So when we think about, the reason why I'm pointing this out is it's going to be helpful in terms of graphing. If we're given a function and we want to graph the first derivative and the second derivative, to understand, well, the second derivative actually is the first derivative of the first derivative. So knowing that relationship can help us understand the relationship graphically. Another way to think about it, remember, like rate of change. So it's slope, it's rate of change. So let's look at the fourth derivative. So the slope, or the rate of change of the third derivative, is 24. It's constant because this is a line. We should know that. That should make sense. But that's something you always want to think about. Remember, derivatives always go back to slope and rate of change. Okay, so I want you to take a minute and pause the video and find the second derivative of this function. Unpause when you're ready to check. Okay, so hopefully you ended up with the second derivative is f double prime of x is negative 4 over the quantity x plus 1 cubed. How did we get that though? Alright, let's look back up here. So first I did the quotient rule. So remember, talk through it. Bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. Good. Now, in order to do the second derivative, though, we do want to simplify this as much as we can before we start the second derivative. Otherwise, the second derivative is just going to get really messy. So I do distribute the numerator, combine like, so that's the distributing of the numerator, combine like terms, and I get the first derivative, f prime of x, is x squared plus 2x plus 3 over x plus 1 quantity squared. Now, in this case, I actually decided to multiply out the denominator as well. You don't need to. It's just that way I think it's going to make the second derivative a little bit easier. So I multiplied out the denominator, so now I'm using this version. So now I do the quotient rule again, so bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. I have to multiply out the whole numerator here. A lot of things combine or reduce, and then I'm left with just negative 4x minus 4 over the quantity x squared plus 2x plus 1 squared. But this is actually x plus 1 to the fourth. So then I end up with negative 4 over x plus 1, or I'm sorry, negative 4 times x plus 1 over x plus 1 to the fourth. The x plus 1's reduce, and that's how I get negative 4 over x plus 1 cubed. Alright, so higher order derivatives are just derivatives of derivatives. The only application that we've seen so far to this, but it is an important application, is understanding that the first derivative of position is velocity, the second derivative of position is acceleration. So in the context of position, velocity, and acceleration, we know that the second derivative of position is acceleration.